So welcome everyone to the ACEAS Seminar of the month. It's my pleasure to introduce Rebecca McGirr, who is a new postdoc for the ACEAS Centre. Beck submitted her PhD in mid-March this year, and last week was told that it has been accepted without modifications. So it's my pleasure to introduce Dr. Rebecca McGirr. The talk she's going to be giving is not on her PhD. It's actually, she's hit the ground running and she's been delving into the analysis that we've done in the recent past on our GRACE solutions, picking holes in it, finding fault and finding solutions to resolve the problems that exist. So I'm really looking forward to this talk. I like people poking sticks at our work and making it better. So, Beck.
Thanks, everyone. Thank you, Paul, for that lovely introduction. As Paul said, I've been working on my postdoc now for a couple of months and thought it was a great idea to present some new research today, but that turned out to be a little bit ambitious. So a lot of what I will show today is very much so in the preliminary stages. So take some things that I say with a grain of salt, but I hope you enjoy it nonetheless. So for those who are not familiar with the GRACE and GRACE follow-on missions, the GRACE mission, which stands for Gravity Recovery and Climate Experiment, was launched in March 2002 and decommissioned in October 2017. Over that time, almost a near continuous time series of temporal gravity field models were produced for about a 15-year period. There are a number of processing centers that take the raw data from the GRACE and GRACE follow-on satellites and turn those into temporal gravity field models using a variety of techniques. We at ANU are the only ones in Australia. After GRACE was decommissioned, the GRACE follow-on satellites were launched in May 2018. They're near replicates of the GRACE satellites with a few modifications. And we've been getting temporal gravity field models from those for about 4 years now. So the GRACE and GRACE follow-on satellites, they, see if this is going to work. I have some problems if videos don't work. Okay. So the GRACE and GRACE follow-on satellites measure the inter-satellite distance between two trailing satellites that follow each other as they orbit around the Earth in a polar near circular orbit. They sit about 200 kilometers apart from each other, and they're about 400 kilometers in altitude. The main instrument that is important for getting the data that we need to turn the GRACE and GRACE follow-on data into temporal gravity field models comes from the K-band ranging instrument, which measures the change between the satellites with a dual microwave ranging instrument, which measures the phase shift of K and Ka band microwave signals that are sent between the satellites. This measurement is accurate to about 1/10 of a human hair. The GRACE follow-on satellites also were fitted with an additional instrument that also measures the intersatellite range between the satellites as they orbit around the Earth. This is the laser ranging interferometer, which was added to the GRACE follow-on payload as a technology demonstrator. And since GRACE follow-on has been launched and analysis has been done on those data, it turns out that the laser ranging intersatellite ranges perform about an order of magnitude better than the K-band ranging instrument. Another instrument that's important for getting these temporal gravity fields is the star cameras, which measure the orientation of the satellites with respect to the stars. And then that information is used both on board the satellites and in post-processing. And finally, one of what I think is one of the most important instruments is the accelerometers, which measure all the non-gravitational forces that act on the satellites, which perturb their orbits and therefore aren't related to the changes in the temporal gravity field. And these can include things like atmospheric drag, solar radiation pressure, Earth albedo, and any of the real linear accelerations that occur due to mistimed thruster firings. So as I said, the GRACE and GRACE follow-on satellites orbit around the Earth at about 400 kilometers altitude in a polar orbit so that they have full coverage of the Earth. They have they repeat their orbit about 15 times a day. And from the data that we collect from GRACE and GRACE follow-on, we use about a month's worth of those orbits to generate temporal gravity field models. The temporal gravity field models contain information about any hydrological changes, so the essentially movements of masses of water around the globe. So hydrology being soil moisture, surface water, groundwater, ice sheet mass change, sea level rise or fall, but also the GRACE and GRACE follow-on satellites measure, they can record accelerations induced by particularly large earthquakes and glacial isostatic adjustment. And this is just a video showing how the satellites vary in inter-satellite range as they fly around the Earth. So as they approach larger masses, the front satellite, the leading satellite will speed up, and that range will increase between the satellites. And as they fly over, you sort of get a mirroring of that pattern. So within those inter-satellite ranges, if we look at this map, which is termed the Himalaya map, it was one of the first data products that we got out of the GRACE follow-on mission. And what you can see is the changing distance between the satellites as they complete an orbit around the Earth. And between 9 and 10 here, you'll see the variation in the intersatellite range as they fly over these mass variations. Within these big wiggles are smaller wiggles that contain information about the parts of the temporal gravity field that we're interested in, such as water masses moving around the Earth, glacial isostatic adjustment, and earthquakes. So one of the most substantial results from the GRACE mission has been the measurement of ice sheet mass change on both the Greenland ice sheet and the Antarctic ice sheet, but also many smaller glaciers and ice-covered areas. Across the GRACE mission, we saw mass loss increase at an accelerating rate in West Antarctica. But in East Antarctica, we saw the area including and surrounding the Totten Glacier lose significant mass. Meanwhile, parts of East Antarctica around Queen Maud Land increased significantly in mass along the coast due to increasing snow accumulation. So one of the things that is potentially problematic about GRACE is, not problematic, that's probably not the right word to say, but if we compare GRACE and GRACE follow-on solutions to things like ice height changes from satellite altimetry. You'll notice that we don't quite get the spatial resolution that we can achieve with satellite altimetry. And there's been a lot of work towards trying to increase the ability to achieve higher spatial resolution from the GRACE and GRACE follow-on data. What you're seeing here is satellite altimetry, trends in changing ice heights from satellite altimetry on the far side there. And then in the middle, Goddard Space Flight Center are one of the processing centers that produce monthly solutions from GRACE and GRACE follow-on data. They do that at a monthly time period, which is the standard across all of the processing centers. And what you'll notice in that middle plot there is that the signal of mass change across both the Greenland ice sheet and the Antarctic ice sheet looks particularly smoothed, and it doesn't quite reach, it's a bit attenuated. It's not quite reflecting what we expect given the results from satellite altimetry. What Goddard have managed to do is produce a high resolution trend solution, which is this one here, where they use all of the GRACE and GRACE follow-on data. Actually, I think this is just GRACE. They use all of the GRACE data and they just solve for a trend across the entire period. So in doing that, with all that extra information, they're able to achieve higher spatial resolution, plus by tweaking their strategy for processing the data itself. You'll notice that, especially in West Antarctica, we pick up a lot more high resolution variation comparatively to this middle plot. And that reflects quite well the spatial pattern that the ICESat has when averaged across these 1 degree by 1 degree grids. So in order to produce those temporal gravity field models at a monthly resolution, we have to go through several steps, and they're fairly general at the start, and then the centers tend to diverge a bit in the way that they parameterize their temporal gravity fields and so on. So I'll just run you through the rough process for how that happens. Essentially, the first step is to compute the theoretical orbits, which are the orbits of the satellites as if the temporal gravity field was unchanging. So if we can include all of the known forces that act on the satellites, or that can be modeled particularly well, such as the gravitational attraction of the sun, moon, and planets, the mean gravity field being the geoid and topographic changes, any atmospheric changes that we don't want to include in our temporal gravity field models, as well as high frequency ocean tides and currents, and the non-gravitational effects that perturb the satellites. So we include all of those in a background model and exclude the temporal gravity field. So from that, we then end up with two sets of orbits, the modeled orbits that don't include the temporal gravity field, and the real orbits that do include all of these accelerations plus the temporal gravity field. In order to extract the signals that are caused by the temporal gravity field, what we do is take an observed minus computed of the intersatellite prefit ranges, and that includes the unmodeled gravity signals. So you can see here that as the ground tracks fly over the Amazon, we're getting signals here, but also West Antarctica, Alaska, Greenland, and so on. And then once you stack up a month of those ground tracks, you can see even more of that signal. We then invert those pre-fit residuals to produce adjustments to our temporal gravity field parameters. What we do at the ANU is use mass-cons, which essentially are just basis functions that are like tiles that cover the Earth, and we estimate a change in height of water across each of those mass-cons in our inversion. When using mass-cons, you have to regularize those parameter adjustments, because otherwise noise from the instruments, noise from error from background models can seep into those parameter adjustments and give you an answer that looks absolutely nothing like what you would expect. So there are a million ways that you can regularize these solutions, and playing with those million ways has been the bane of my existence for some time. Last year, our group published a GRACE time series of monthly temporal gravity field solutions. And in that publication, we decided on this as our regularization scheme, whereby we pick model uncertainties that are geographically related to how much we expect those regions to vary on a month-to-month basis. So obviously, we expect areas that are covered in ice to be varying significantly month to month, as do we expect the Amazon and places like the Caspian Sea to be varying significantly. So we want to be able to let those parameters adjust during the inversion, but tighten up areas like the ocean, which don't have as much, like they don't have that same amplitude and signal. And if you leave those open, then noise just flies in and gives you a very stripy solution. Because of regularization, being that it damps the adjustments to the parameters, we have to iterate so that we don't leave any of the temporal gravity field signal in the post-fit residuals. So as you can see here, moving from eta0 to eta3, we update the parameter, the mass-con parameter adjustments successively in each iteration. We end up with much more signal in places like the Amazon after those successive iterations, with the hope that between eta2 and eta3, we've sort of converged on a solution. We don't get any adjustments after that. Iteration can be particularly important around areas of very high mass change. So in West Antarctica, for example, you'll see in our eta0 solutions, we end up with a lot of leakage of signal across the coastline. And with successive iterations, we put that signal that is actually occurring on the ice sheets back onto the continent and clean up that ocean a bit. So the result of all that work, published in JGR end of last year, early this year. These are our GRACE solutions. You'll notice that some months look good, other months look a bit stripy. Other areas like West Antarctica and Greenland look a bit what I call speckledy. Signals that don't really make a lot of sense do seep in, especially once you get towards the second half of the mission, when a lot of the instrumentation started behaving not up to scratch. So we have more noise to contend with in those pre-fit residuals, and therefore we need to regularize more, but we also have more signal that we need to allow into the parameter adjustments. So it's a bit of a push and pull with trying to not attenuate the solutions, but trying to not let noise creep in either. So since we published these, I've had problems with how some of these solutions look, especially the ocean signals. But if we look at it on a time series basis, pulling out the integrated Greenland, Caspian, and Antarctic time series and comparing those to the results from other processing centers, they're actually pretty good. We match really well in most areas. In the ocean, however, we were picked up for having too large of an amplitude on our seasonal signal. We also overestimate the mass increase comparatively to other solutions. So recently we've started diving into comparing our published solutions to satellite altimetry. Up the top here is just sort of a close-up look at West Antarctica, where I've got change in ice height on the far side there. And then that signal averaged over the Goddard Space Flight Center mass cons, which are 1 degree by 1 degree, and over our mass cons, which are irregular in shape, roughly 200 kilometre by 200 kilometre. The reason we do that is so that we can move around the coastlines rather than having overlapping mass cons with the coastline and potentially leaking signal into those areas. So the GSFC mass cons and the ANU mass cons, as I have them plotted up here, are just this Shepherd et al. Trend. The Shepherd et al. Trend averaged over the two different mass con sizes. So if our solutions were producing the correct signal, assuming that satellite altimetry is the gold standard, then this is what we would hope to get out of our solutions by computing a trend from all of our monthly solutions. We don't do a terrible job. I've got our mass cons here plotted, and what you can see is along the coastline, we're hitting the areas that are showing major mass loss. But then once you sort of creep in from the coastline a little bit, we're getting some flipping mass cons that maybe don't quite correlate to real signal and may instead be due to correlations between the parameters. For example, if you look at this line here, just the line inland from our coast-hugging mass cons, we get these areas of mass increase which don't look like they exist. We also get another area of mass loss, which again doesn't really, when comparing to satellite altimetry, doesn't look like it's real. So what we've done since looking at that is just doing a sort of randomized pick a mass con, plot up the time series of our mass cons and compare them to the changes in ice height from satellite altimetry. So here's an example where we're not doing too bad, apart from an offset, but otherwise we're matching that trend really well. This is pretty much the case for all of the coastline hugging mass cons. They, for some reason, possibly because they have less correlated parameters around them, because they're abutted to the ocean, I'm not sure, but they seem to be doing okay. Once we move a bit inland, we see a couple of interesting things. The first being that we're seeing mass increase in areas that satellite altimetry is not seeing much change in ice height, and potentially a decrease in ice height. We're also seeing these weird jumps between our GRACE and GRACE follow-on solutions. For our published solutions, these come by quite regularly. If you're just randomly picking a mascon to plot up the time series of mass change, it's pretty hard to avoid finding these weird offsets between GRACE and GRACE follow-on. So another thing about GRACE and GRACE follow-on solutions is that the GRACE community has never been able to estimate the change in the equatorial bulge of the Earth, which is the C20 spherical harmonic coefficient. And it just looks like this example here. So just that changing bulge, which varies at a seasonal time scale. And instead we replace that signal with estimates from satellite laser ranging, which you can see plotted behind the pink and the red in the gray. They get a nice seasonal signal. Our published solutions, which are the red, pretty much get no seasonal signal whatsoever. And on top of that, we have this kind of 7-year period that pops in, which we haven't been able to attribute to anything. The pink line behind there is the zero solution, so with just 0 a priori mascon parameters. And then the red is our fully iterated converged solution. Now, my main problem with this is that there is a poster that sits at the front of my office from 2017, one that Paul presented at AGU. And on that poster, there is this beautiful plot of our C20 time series where we beautifully match the satellite laser ranging estimates of the C20. And for some reason, with time, we had lost that ability to estimate the C20. This is particularly important because pretty much no other centres are able to estimate this coefficient. Others have sort of guessed as to why that might be, but they're all pretty accepting of it, and instead just after they've finished processing their time series, they just come through, make corrections like glacial isostatic adjustment and that sort of thing, and also replace this equatorial bulge. Anyway, so I wanted to figure out what had happened between 2017 and 2022 that we could no longer estimate this signal. The difference between those 2017 solutions and our 2022 solutions were a number of things. We'd made a million code changes during that time, so I thought I might have been digging myself very deep into a rabbit hole. The two easiest changes to test were that we had different mascon sizes, so we were using 100 kilometre by 100 kilometre mascons at the polar areas where there's higher ground track coverage and more repeat orbits. So presumably more data to strengthen the estimates that you can get from places like Greenland and Antarctica. Since then, we've moved to having 200 kilometre mascons everywhere, just for consistency more than anything. We also completely changed the way that we regularized our solutions. So what we did back in the day was we had these values on geographic regions, but very broad, just 4 different values. So ocean, land, Antarctic ice sheet, and Greenland ice sheet. And we also applied a regularization parameter to our regularization matrix, which was equal to the number of days, with the explanation that it was reasonable to do that because we would need stronger regularization the more days you added to the inversion, because you have more days of noise entering your prefix residuals. So luckily for me, it turned out that the regularization that we'd started using to produce our recently published solutions was the culprit of those changes. Actually, I think that's that. Yeah, so the pink behind here, which is an either zero solution, so zero a priori on the MASCON parameters, and the violet purple is the exact same orbits, the exact same normal equations that we invert, just with a different p and a different lambda. And that's all we had to do to get this beautiful C20 series back. With a slight issue. While we could get that C20 time series, looking at our time series for global mean sea level and also the Antarctic Ice Sheet, keeping in mind that these are uniterated MASCON solutions, so we expect there to be some attenuation of the gravity signal. But now we were achieving far less of the seasonal amplitude and trend on these large integrated regions, which previously, even in our uniterated 200-kilometer, not so well regularized solutions, we were actually hitting those time series pretty well compared to other processing centers. So looking again at the trends over our MASCONs, the one on the far side there being our published solutions turned into a trend, and the one closest to me being these as once iterated, so an iter1 solution, using these different regularization constraints. And some great things about that being that we are not getting these regions of mass increase just in from these coastline hugging MASCONs that, according to other GRACE and GRACE follow-on solutions and satellite altimetry, isn't real. We're also not getting these regions of mass increase further inland, which also, according to satellite altimetry, doesn't exist. So that's great. But obviously we're attenuating the signal right alongside the coast there. We assume that with iteration, this would go away. We would increase that trend without reintroducing these areas of weird mass increase, mass loss that don't correlate to the altimetry. But that's yet to be seen, as we've yet to properly iterate on these solutions and produce a final converged time series. Picking out one of the MASCONs that I had before, which was one of these coast hugging MASCONs, you can see that, you know, we're getting mass loss, but it is considerably attenuated compared to satellite altimetry. So I thought that was great until I kept picking, and I found a couple of places here and there that I didn't like so much. So in some cases, we are still getting this weird increase towards the end of the time series, where you would expect this trend to just continue down and then join up with GRACE follow-on, rather than flicking up and then having this offset. We're also seeing some MASCONs that are total odds to the satellite altimetry. And in cases like these, you can probably only expect that, you know, iterating on these values as the a priori MASCON values is probably not going to solve that problem. So we've done some tests on looking at larger MASCONs with the assumption that our problem here might be that we have two smaller mass cons that are highly correlated, and they're producing these estimates that sort of complement each other. And when you integrate them, they give you the right signal across an area as large as the Antarctic Ice Sheet or the Greenland Ice Sheet or across the whole ocean. But when you pick out these individual mass cons, you just can't get that spatial resolution. That's not to say that we're unlike other centers, because pretty much everyone who uses mass cons to do their temporal gravity field estimates will say, you know, we use 1 degree by 1 degree mass cons, but that's not the spatial resolution. The mass cons are correlated spatially. We more have a 300 kilometer, maybe 400 kilometer spatial resolution. But, you know, I think with the right processing strategy, we are probably able to improve this with a smart way for creating our a priori parameter values and using the right size mass cons and the right regularization strategy, which, as you've seen, can have such a huge impact on things like the C20 time series. My question from here is, are we able to estimate a good C20 time series while also estimating a mass change over the ice sheets that's comparable to other centers and with satellite altimetry, or is it a bit of a give and take? You sort of just have to pick which one you want to hit, which in most cases, you want to be able to actually produce good estimates of the temporal gravity field, being, you know, ice mass loss and hydrology signals and everything else. So that's where I've gotten to with that. I've also recently tried to have a quick look at our GRACE follow-on solutions for this year, which, you know, they sort of get produced automatically as the data comes in about 3 weeks after the fact. We get our automatically generated GRACE follow-on time series. And like the GRACE series, there's a lot of flaws in them, and I'm picking that apart with things like how it produced our a priori models and stuff like that. There's a lot of improvements to be made. But given what we had, I wanted to have a look at what GRACE follow-on is telling us over the East Antarctic heat wave, which happened in the middle of March this year. For about a week between, I think, the 15th to the 23rd of March, there was a massive heat wave that hit East Antarctica with temperatures hitting about 40 degrees higher than the anomaly in some regions, peaking at around the 18th of March. With that came lots of precipitation in the form of rain and snow. Being that it was March, temperatures didn't really get above freezing, so there wasn't a bunch of melting, but also there's contradictory, people are saying contradictory things at the moment. This, you know, only happened very recently, so there isn't any published results on this event yet. So having a look at our GRACE follow-on solutions. The top row is using our published style regularization, so where we're getting those integrated time series correctly. And the bottom is using our new regularization approach based on our 2017 regularization approach, which produced the good C20 time series. You can't see a lot in these plots. I've just plotted up February to March and the difference between February and March, hoping that I would see some sort of mass accumulation around East Antarctica that would be correlated to the massive amounts of snow that fell over that part of the continent during this heat wave. And they're sort of a bit stripy, so I'd take these results with a grain of salt. But what we do see when integrating the mass change across the entire Antarctic ice sheet, depending on the regularization strategy used, and obviously these values would change when iterated on and ending up at a converged solution, which would hopefully not be too different between these two approaches. We do see about somewhere between 200 and 400 gigatons of mass increase across the entire Antarctic ice sheet between February and March. So again, whether or not that's related to that event is to be seen, but I think with improved grace follow-on processing, we'll be able to interrogate these events a bit closer and actually see what their effects have been. So I was going to write conclusions in future work, but there's just so much to be done that I didn't bother. But obviously, the priority at the moment is to try and see if I can develop some sort of processing strategy with a combination of regularization, changing up the regularization styles, looking at different size masscons, looking at how we build our a priori masscon values that we then iterate on, trying to see if there is any possible way we can develop a strategy that is going to achieve a good C20 estimate, but also mass change time series over Antarctica and Greenland and everywhere, the Caspian Ocean, that actually match the other centers as well, and therefore our published solutions. I'm not sure if that's possible. I would like to think that it is. And I think that if we can manage a solution that hits all of those things, then that will be pretty impressive in the scheme of things. In addition to that, I'm looking at, in the not too distant future, hopefully, I sort of need to get a good time series of grace and graceful and temporal gravity fields first before I can attempt diving into this. But what I want to eventually do is to produce a time series of glacial isostatic adjustment from grace and graceful on data alone by playing around with the way that we utilize masscons, putting them at different heights, looking at different types of ways to constrain those parameter adjustments. But yeah, there's lots to be done. This is the very beginning. It's only been a couple of months and I feel like there's a lot of work already in front of me. So thank you very much for coming today. Thank you for joining online.
Thanks, Beck. I think it's an amazing amount of work in just a couple of minutes. Does anyone have any questions? Dave.
So I can appreciate the difficulties of trying to come up with parsimonious regularization on these kind of problems, but the other aspect is that you're also assuming a quadratic loss. Is that appropriate? And does physics tell you that's the best way to represent the difference between your model and the data? Because by itself, that is going to tend to emphasize the noise.
Yeah.
And maybe using an alternative like the L1 wall or something like that, it's known to be more resistant to noise. It's maybe a better way to actually find the optimal solution.
Yeah, I haven't considered that, and it's probably worth diving into, definitely, because yeah, I think regularization, that, like I said, there's a million strategies, and everyone does it sort of slightly differently.
Yeah.
Whether, you know, with imposing correlations between mass cons, imposing correlations with time, not imposing correlations at all. Yeah, I wouldn't mind diving into something different because
quadratic loss is very mathematically convenient, but not necessarily physically realistic.
Okay.
Yeah.
Thank you. I appreciate that.
Tony?
So with your regularization, shouldn't it be time dependent? Because the further you are from your mean gravity field, the larger a variation you expect. If you've got the same sigma values, then you're suppressing the more removed perturbations, and that may be a part of why you're seeing that attenuation.
Yeah.
As you get later and later, you might consider sort of a temporal adjustment.
Yeah, absolutely. And that's been on my mind. I didn't mention the problem of what our mean values are. They're calculated over the period of 2008 and 2010 to produce a static gravity field model. So then all of the variations in our, we're trying to adjust these mass con parameters against 2008 to 2010 values. And once, we're in 2022 now. So we're getting in our third iteration of the Grace-Follow-on solutions, we're seeing over 11 meters of mass loss in some mass cons in West Antarctica. And it would be ideal to figure out some sort of way to vary. I think probably the temporal variation, I would like to see come through the regularization parameter rather than the sigma values. Because I think that's sort of more justifiable, and there are different ways that you can find an optimized value for that parameter. When just looking at the GRACE time series itself, you get into 2016 towards the end of the mission, and you're getting significantly large adjustments in areas with significant ice sheet mass loss, but there's also additional noise coming from the degradation of various instruments. So sort of need to really beat that noise down, but at the same time try to not attenuate those large signals that you're expecting towards the end of the time series as you move further and further away from that average value.
One of the problems you were getting was attenuation, which would be explained by the fact that it's just denting the signal that's not allowed very much.
Yeah, in some instances I was saying, I didn't plot those up there, but in some instances it wasn't sort of consistent across all mass cons. We were seeing attenuation and then mass increase that was just flying up. Which I need to look at it a bit more. But I think varying that regularization parameter is probably the way to go.
Adele, are there questions online?
Yes. Martin Yucca has a question. Do you want to try unmuting Martin and asking?
Yes, I'll try. Thank you. Does that work?
Yeah.
Yeah, cool. Thanks, Rebecca. I've got a very naive question from somebody who knows nothing about these things. Why you've always compared to like better data sets like satellite altimetry or what other centers are doing. So why do you need your own? Why can't you just use data from the other centers?
Yeah, that's a really great question, because I think at the heart of that is we think we can do it better. We just haven't proven that yet. We're using two sort of parts of our processing strategy are unique compared to the other various processing centers around the world, in that we use these irregular shaped mass cons so we can fit those mass changes along coastlines really well when we get the regularization back. And also we use the range acceleration as the intersatellite observation, which I think I showed it early on in this talk. Up here. So this is the pre-fit range acceleration residual, where you can pull out those signals that are coming from the unmodeled temporal gravity field really well. Most other centers are using range rate as their intersatellite variation, which sort of, it has a once per orbit additional signal. You can't really pull out these temporal gravity signals right from the pre-fit residuals. And it introduces more north-south striping. So by using the range acceleration, we're improving that north-south striping issue. Yeah, so there's a couple of things that we're doing that we think if we get everything else right, we're going to be able to produce a really good grace fallen time series. But we're in the early days of doing that. And, you know, it's nice to be able to get in and actually make decisions on how it's being processed and not to be sitting back and thinking, I probably wouldn't do it that way. So that's my justification.
Yeah, cool. Thank you.
You're welcome.
Could I just ask to follow on from that one? So I guess that kind of explains it doing better than the other GRACE centres. But I mean, do you expect to be able to do better than altimetry at some point, or measure things differently that altimetry can't measure?
Well, obviously with GRACE and GRACE follow-on, we're measuring the mass change directly, so we're not relying on Fern compaction models and things like that. And we've got greater temporal resolution. So I don't know if we expect, I mean, I absolutely don't expect to ever get greater spatial resolution than satellite altimetry. But I think mass change missions are here to stay. After GRACE follow-on, there'll be another one launched called the mass change mission. And yes, we have satellite altimetry in areas like in ice-covered regions, but for places where those changes aren't visible at the surface, yeah, GRACE and GRACE follow-on are really great for that purpose. But yeah, I can't say I expect to get better than satellite altimetry in a spatial resolution sense.
Great, thanks. There's no more online questions at the moment, Paul. If there's any more there.
More questions in the room, Matt?
Yeah, Beck, thanks, and you have done a lot of work in 2 months. So those mass cons that you show that go really crazy at the end of the GRACE period, and then there's an offset.
Mm-hmm.
When you look at the surrounding mass cons, is that apparent mass change going somewhere else? Do they cancel out from larger areas?
Yeah, and some they do. Yeah, you can.
In some, but not all.
In some, but not all. I mean, I've sort of done this in a way where it's just like, look at this one mass con, look at the mass cons around it. How are they changing? Are they showing opposite signals that are equivalent in magnitude? And yes, they are. So it's a correlation problem. Others deal with that by imposing constraints in some spatial radius around their mass con parameters. But our argument has been that that further attenuates the signal. And looking at, where's my mouse? So if we go back to this image from Loomis et al. So the middle one there, their monthly solutions, where they've computed a trend from their monthly solutions, are computed, they're regularized using a spatial constraint. So we think that that furthers the smoothing and attenuation of those signals compared to what you would expect from the satellite altimetry averaged over those mass cons. To create their high resolution time series, they didn't impose those spatial constraints, but otherwise their processing was fairly the same. Their argument being that they had so much data from the entire time series that it wasn't necessary to impose those spatial constraints. So yeah, I mean, if we can manage to do it without imposing those spatial constraints for each month, then potentially we'll be able to get a higher spatial resolution monthly time series. But then there's the issue of having highly correlated mass cons.
So you're trying to have your cake and eat it.
Yeah, exactly.
We have one more online question. Roland Warner, do you want to try unmuting and asking?
Hi, thank you very much. Very interesting talk. I had two questions that I wanted to put to you. The first was, my understanding of regularization is constraining how much you are allowed to play around with the tuning parameters. I wondered whether you'd explored building into that sort of penalty, just the ability to recognize these unrealistic or bad solutions in terms of parameters that give too much of this unphysical stripy behavior.
Yeah. Yeah, we've considered playing around with the way that we build our regularization, including information on mass con correlations just from the unregularized solutions and doing things fancy ways. But I don't think, we haven't really come to anything yet, nor have we tested a bunch of options yet either. It was sort of getting these solutions published in the first place was a long and arduous task. But now we can come back and look at what we've produced and try to come up with more optimal ways of doing that. So yeah, I think there's probably a long road ahead in testing different ways to regularize the parameter adjustments.
Thank you. My second question was really about, which is somewhat more speculative, is about your East Antarctic heat wave story. One suggestion was that it might also be interesting to see what the data for April looks like.
Yeah.
If that snow has fallen, it won't have gone away.
Yes.
The other issue, the other question is there any, perhaps it's too early, is there any information yet about estimates of precipitation from atmospheric circulation models?
So first part of that question, I really wanted to include April, but we only had about half of the month processed. So I didn't want to include that with half the amount of days and, you know, potentially be making conclusions of a not great month of solutions. Second question is, I know there's been models, climate models run on that, on the East Antarctic heat wave, and estimations made on how much precipitation fell over that period. I think I remember I can't remember, 65 gigatons or something over a few days of snow in East Antarctica. But yeah, again, it happens.
Well, there was a lot of talk about atmospheric rivers and so forth.
Yeah.
Something which probably spoils your normal processing chain, but given that this peak event was in the middle of March, is it sufficiently interesting to be worth doing 30 days before and after that event? I mean, if that event's in the middle of March, it's not clear how good the calendar month March solution is in answering this question.
Yeah, we can play around with doing solutions with a different number of days in them. I don't think our grace follow-on processing is up to scratch for producing like 10-day solutions, which we can do with grace data when the instrument's behaving and we've got good ground track coverage. I think once we've sort of polished our processing on the GRACE. Follow on, I'd like to then come through once I've got a few more months on the other side of March 2022 and do some 10-day solutions and see if we get spikes when we expect to see spikes over that heat wave. So I wish.
Yeah, simply that even on monthly solutions, simply shifting the time frame to be before and after that event, which should give a sharper.
Yeah.
Anyway, thanks very much.
No, that's okay. You're welcome.
That actually highlights the reason why we're doing this ourselves, because we have the flexibility to do this.
Yeah, that's right.
It's 11 o'clock. Sorry, it's 2 o'clock. 11 o'clock. So please join me in thanking Rebecca again for a great talk.